Welcome to the General Chemistry Fundamentals series presented by MCAT Genie. In today's video, we're going to talk about intramolecular bonding and intermolecular forces. If you were to travel within one state, you would say that you are traveling intrastate. And if you were traveling between states, and let's say you were to do a crime, that would be considered a federal crime because it is interstate. Intra means within a molecule, so the bonds that create a molecule. And intermolecular means that these are the forces between molecules that already are bonded together. So we're going to focus on intramolecular bonding first, and this brings us back down to our handy-dandy electronegativity table. So the electronegativity values here are going to represent, as we've seen before, that our effective nuclear charge is going to be highest in the top right. So the highest electronegativity is fluorine. Second is oxygen. Third will be considered nitrogen. And in the bottom left, we'll have our cesium and francium, for example, alkali metals with very low electronegativity. And remember, as a definition, electronegativity is the tendency for an atom to pull or attract electrons when in a molecular bond. Your job is not to necessarily memorize these values, but your job is to know the relationship between electronegativity differences and the type of intramolecular bonding that we should expect. So this table does a great job of showing us how, as the electronegativity difference between two bonded atoms increases, we're going to move from nonpolar covalent to polar covalent to ionic bonding as the electronegativity difference increases. And we'll explain what each of these bond types means. What does nonpolar versus polar mean? What does covalent bonding mean? And what is ionic bonding? I want you to just associate nonpolar instead of the term pure covalent because that's the term that we're going to be using more often. I rarely have ever seen pure covalent, but this diagram still does the job. The key to understanding why bonding occurs is understanding that molecules and or bonds form when they can achieve a lower energy state than when they were isolated or individually separated. You can see from this diagram that when the hydrogen atoms are too far apart, they have no interaction because they're not close enough to achieve a lower energy state. And once they're at their optimum distance, which is going to be this bond length, then we're going to form H2 as a molecule. There are three types of covalent bonds. The first is a single bond, as you can see all the way to the left. This is going to be between H and Cl in this case. A single bond only consists of one sigma bond and no pi bonds. We'll go into further detail about sigma and pi bonds in a different video. Just accept the definitions for the time being. Two oxygen atoms will form a double bond, which will include one sigma bond, and the double bond, or the second bond, is going to be the pi bond. And in the case of two nitrogen atoms, we're going to have one sigma bond, and the other two bonds within the triple bond are also pi bonds. The term covalent means to share electrons. So co meaning together, and valent representing that they are sharing their valence electrons. The key word is sharing. As I said earlier, briefly, the electronegativity difference between carbon and hydrogen is 0.4 or less. Therefore, the bonding here is known as a nonpolar covalent bond. This means that even though carbon is slightly higher in electronegativity than hydrogen is, we can't assign a permanent dipole, meaning one side has a positive partial charge and the other side has a negative partial charge. That's what the poles stand for. So in the case of carbon and hydrogen, there is no significant dipole, which this arrow here would represent what's known as a dipole moment. But there is not enough of an electronegativity difference for there to be a permanent dipole. That concept becomes very important when we talk about solubility and when we talk about waterproofing things, for example, like a cell membrane would need to do. When we're talking about polar covalent bonds, these form because we typically have two nonmetals, which are not different enough in electronegativity, where it's greater than 1.7 or 1.8, but instead it falls within the range between 0.4 and 1.7, let's say, where one of the atoms is significantly different than the other atom when it comes to electronegativity, in which case fluorine is significantly different from boron. And because fluorine is the more electronegative side, that atom will be considered the partially negative atom within the molecule, and boron will be considered partially positive. If you're wondering what this symbol is that I drew, this is the lowercase Greek letter delta. Therefore, with polar molecules with polar covalent bonds, we can say that there is a permanent dipole. When there is a polar bond, such as in hydrochloric acid, also known as HCl, you're going to notice that the more electronegative atom will attract the majority of the electron cloud density. So that means that the majority of the electrons are surrounding chlorine rather than hydrogen, because chlorine has a stronger pull on the electrons in the bond than hydrogen does. At some point, we will discuss how even though the bonds within a molecule can be polar and there can be dipoles which are permanent, the molecule as a whole may be considered nonpolar. A great example of this will be carbon dioxide. What happens in carbon dioxide is that because it's a linear molecule with two double bonds and the dipole moments are completely 180 degrees opposing each other, the vectors end up canceling out, and this leads to an overall nonpolar molecule. This is a concept that I will talk about more when we go into VSEPR theory, molecular geometry, and polarity. In this table, you can see the naming conventions for some of the molecular compounds that are composed of two elements. Typically, what you're going to do when you're naming covalent compounds is you're going to look at the first atom, and you're simply going to start with the name of the central atom or atoms. And if there are multiple, then you're going to say di if there's two, tri if there's three, tetra if there's four, penta if there's five, so on and so forth. The same concept will apply to the other atoms that are within the compound if there are two elements, and the suffix "ide" IDE will be added to the end of those. I want to quickly introduce metallic bonding, and the reason why it's important is because with metallic bonding, although there is a sharing of electrons, it does not fall under the typical categorization of nonpolar or polar covalent. The reason for this is because all of the metal atoms are the same, so theoretically it should be nonpolar covalent. However, the sharing of the electrons does not happen because any one metal atom or nucleus wants to hold on to the electrons. In fact, in this scenario, all of the electrons are free to move as they wish. And so metallic bonding is known as a mobile sea of electrons, as you can see. You can expect this type of bonding to exist in metals in their solid form. And this is what makes certain metals very conductive and capable of conducting electricity because the electrons are mobile and have the ability to move. This allows an electromotive force to cause those electrons to move in a certain direction, and this leads to the conduction of electricity. We will talk about this in far more detail when we get to conductivity. Another very common intramolecular bond that you'll have to be familiar with is called ionic bonding, which leads to what's known as ionic compounds. They're typically not called molecules, so if you see something as molecular, normally that's going to be associated with covalent bonding. For ionic compounds, what happens is the electronegativity difference, which is typically between a nonmetal and a metal, is so high or greater than 1.7 or 1.8, there's not a sharing of electrons, such as with covalent. Rather, there's a complete transfer of electrons from one species to the other. In picture A, you can see sodium, which is suspended in an oil solution, because if sodium comes into contact with water or air in its atomic form, it is extremely reactive because it's an alkali metal and can easily lose one electron. In the second picture, B, what looks like oil is really just chlorine gas in its gaseous state. So both sodium and chlorine in their atomic states are represented by A and B respectively, and C represents sodium chloride as an ionic compound, in which case sodium chloride consists of a sodium with a 1 plus charge and chloride with a 1 minus charge. This figure here does a very good job of showing how sodium is going to react with chlorine and form sodium chloride. The point of the bottom part of this figure, part C, is to show that each sodium and chloride ion is not only attracted to one other ion, but is attracted to all of the other ions within the compound. Therefore, there's going to be ionic attraction due to the electrostatic charges of each of the ions in all three dimensions, forward and backward, left and right, and top to bottom. In this version of the periodic table, you can see some of the commonly used ions that we're going to have to deal with, and this is when we're dealing with one singular ion. Here are some examples of ionic compounds and their naming. For ionic compounds, you're going to take the name of the metal and simply put it there as is. It does not matter what count of that metal exists. So even if there are 2 sodiums or 3 magnesiums or 3 calciums or 4 aluminums, the name is still aluminum or calcium or magnesium. You don't need to put mono, di, tri, tetra, penta, so on and so forth. That's reserved for molecular compounds, which are typically covalent. The nonmetal that's bound in an ionic compound typically ends in "ide," similar to before, and the number of nonmetal, or anions typically, that are present are also not mentioned in the name. The number of each ion within a compound is typically determined by the charge of the metal ion and the charge of the nonmetal, which you're supposed to be able to assume in each scenario. If you're dealing with transition metals, as I said before, they can have a number of different charges because they can lose a different number of valence electrons in different scenarios. So if you're dealing with iron 2 plus, then in parentheses, there will be the Roman numeral 2, which will indicate that the charge of iron is 2 plus, which indicates that if it's bound to chloride, which has a 1 minus charge, there should be 2 chlorides and 1 iron. The formula is FeCl2. If it's iron 3 plus, the formula becomes FeCl3. This same trend is going to follow for the rest of them in this table. So polyatomic ions introduce an interesting scenario to us, which is because the polyatomic ions are created from covalent bonded nonmetals, but overall have a net charge. I highly recommend paying close attention to every single one of these polyatomic ions because you will come across it at some point. You're also going to want to memorize the charges associated with each of these and the number of oxygens that you expect. A lot of the acid and base theory involves these types of polyatomic ions. It's very important for understanding the buffer systems of the blood, particularly bicarbonate, carbonic acid, phosphoric acid as well, and be able to draw out their structures, their bonding between their atoms, and why they have an overall net charge. Please refer to the Lewis dot structures video for help with that. The last type of intramolecular bond that I want to talk about is called coordinate covalent bonding. The reason why coordinate covalent bonds don't fall under any of the specific categories that we mentioned before is because when you're dealing with a coordinate covalent bond, we're typically dealing with a transition metal that has a positive charge on it. So it could be a mono, di, or polyvalent transition metal. When these transition metal cations come into contact with electronegative atoms, typically nonmetals, that are already participating in covalent bonds, so they don't have an actual charge, positive or negative, but they have a partial charge, typically partially negative. So if we zoom into the heme group, you can see that the porphyrin ring, which is the organic ring that surrounds the iron, it consists of 4 pyrols. We'll talk in more detail about how do you name nitrogenous heterocyclic aromatic compounds. But for now, I want you to focus on how the nitrogens all will have lone pairs. Because they all have lone pairs, that means that they have pi electrons. The thing about the iron here is that the iron is the only thing here with an actual positive charge. This means that the iron has ionized, lost its electrons to the solution most likely, and has an actual positive charge on it because it lost 2 electrons. This ends up becoming important for carrying oxygen, which we'll focus on that more when we get to the circulatory system. But in the case of heme, the iron is capable of holding the porphyrin ring together and giving it structure because the nitrogen atoms are donating their electrons to the iron, but it's not a full transfer, so it's not ionic because the nitrogen doesn't form a charge. So the nitrogen technically is sharing its electrons with the iron, and the iron is only sharing its positive charge in return. I think that this is similar to having a friend who doesn't have a living arrangement but needs your place to live. So let's say it's your couch or an extra bed. So basically, you're sharing with them, but you're not asking the friend for money in return. They're just sharing their positivity with you. I know it's kind of a silly analogy, but it really does help with understanding how the coordinate covalent bonding occurs, why it's not exactly ionic, but also why it's not exactly covalent, and why there's a net overall charge that still exists when we're talking about the coordinate complex as a whole. So I want you to notice from these figures that they all have brackets because the overall complexes share the charge that the central transition metal cation has on it. So I drew in the charges to really represent this. It belongs to the cation that is the central coordinate covalent cation. If you ever see the term coordination number, it just means how many things are coordinate covalently bonded to the central cation. In the first situation, the number would be 2. In the second scenario, the number would be 4. And in the third image, the number would be 6. Whenever you see hydrated complexes, it's usually referring to something similar to the third picture here. Let's move on to IMF, or intermolecular forces now. So the ones that we mentioned already were intramolecular. These are strong bonds that hold molecules together, and the only way to truly break it is to do a chemical reaction. So you have to change the intramolecular bonding with a chemical reaction such as combustion, precipitation, acid-base, redox, so on and so forth. For intermolecular forces, they're all significantly weaker than the stronger intramolecular forces. To break intermolecular forces, raising the temperature, reaching a melting point, reaching a boiling point, increasing the energy, reducing the pressure surrounding a molecule will all influence the intermolecular forces. If something has stronger intermolecular forces, it's more likely to be a solid. As something has weakened intermolecular forces or more distance between the molecules, then you can expect the phase to be more similar to gas. I want to make a clear point that increasing temperature is increasing the average kinetic energy of the atoms or molecules present. Adding heat can lead to and does lead to a change in temperature, but temperature is not a measure of heat. Heat is measured in joules typically, and temperature is measured in degrees Celsius or Kelvin. All of the intermolecular forces that we're going to talk about after this point are known as van der Waals forces, and the definition is that they are weak attractive forces between atoms and molecules. The weakest of the intermolecular forces is known as London dispersion forces. In London dispersion forces, it's not because we have a permanent dipole. In fact, we're dealing with molecules that don't have polar covalent bonding. Instead, they'll have non-polar covalent bonding because they don't have significantly different electronegativities. This means that when these types of molecules come into contact with each other, even though there's no permanent dipole, what happens is known as an induced or temporary dipole. This causes a very weak and brief attractive force between these molecules since there's somewhat very slight of an unequal distribution of the electrons. Every molecule, whether it's nonpolar, polar covalent, or ionic, to some extent experiences London dispersion forces. So this is going to be across the board no matter what molecule we're discussing. These London dispersion forces will increase depending on the shape of the molecule that we're dealing with. This is a very important concept that we'll come across when we get to fatty acids, saturated versus unsaturated. For example, if we're comparing butter, oil, margarine, and different types of fats. And what we notice is that if the surface area is larger, there's a larger contact area. So the larger the molecule is, the stronger the attraction is going to be. But the surface area increases if the molecule is flatter. If there are too many branching points, it will decrease the surface area, and therefore the boiling point will be less. Remember, the more intermolecular forces we have, the higher the boiling point. For the second type of intermolecular force, we're going to mention dipole-dipole. This is going to be the primary, strongest intermolecular force in polar molecules. And the reason it occurs is because polar covalent bonds have permanent dipoles. Therefore, there is a dipole related to each molecule, and they will arrange as such. There's also dipole-ion interactions, where a polar covalently bond molecule, such as water, has an interaction with ions. The interaction between dipoles and the interactions between dipoles and ions influence solubility heavily, especially when we're talking about aqueous solutions. We'll go into more detail about that when we get to solvation shells. Speaking of water, if hydrogens are bound to the three most electronegative atoms that we know of, which are fluorine, oxygen, and nitrogen, then those hydrogens are capable of forming what are known as hydrogen bonds with the other nitrogen, oxygen, or fluorine atoms that belong to the molecules nearby. So this is a large reason why water has a high boiling point, because it's going to include the London dispersion forces, as well as the dipole-dipole interactions, as well as the hydrogen bonding on top of that. Because it includes all of those, it's going to have certain properties which are very unique. For example, water has high surface tension. We know that if you jump into water from a large enough distance, you'll slap the water like concrete. Certain bugs can even walk on water due to surface tension. The hydrogen bonding also improves water's ability to be adhesive and cohesive to other water molecules. The specific heat capacity of water is particularly high. which means that water can retain heat for long periods of time after being heated, and water also remains cold and is difficult to heat if it does not contain a lot of thermal energy. Furthermore, the density of liquid water happens to be higher than the density of ice, which is quite unexpected because ice is a solid. So shouldn't ice sink in water? The arrangement of the hydrogen bonding in liquid water molecules is part of the reason why that's not the case. I won't go into too much more detail about water at this given point in time, but hydrogen bonding is very significant with explaining why water has a high boiling point. It also helps to explain why alcohols have a higher boiling point than, for example, ketones or aldehydes. And finally, it also helps explain how the bonding happens between nitrogenous bases within DNA and RNA. So the thing that's holding the double helix together are really the hydrogen bonds that exist between adenine and thymine and guanine and cytosine. That's our normal expected base pairing. As you can see, adenine and thymine only have 2 hydrogen bonds, whereas guanine and cytosine have 3. This means that nucleic acid polymers like DNA or RNA have a higher melting temperature or denaturing point when they're higher in GC content, meaning guanine-cytosine bonding. This is a concept that becomes very important when we go into different analytic techniques, such as PCR. Just to go into a little bit more detail that will be useful for biochemistry, if the electronegative atom, such as nitrogen, oxygen, or fluorine, has the H already on it, this is known as the H bond donor. And if the hydrogen bond is occurring from the hydrogen with the other electronegative atom, then that's known as the acceptor. I hope this was a useful review of the different types of intramolecular bonding and intermolecular forces. I promise you, knowing how the intermolecular bonding is occurring within each compound is really, really useful for predicting what might happen in a reaction, specifically chemical reactions. And the intermolecular bonds form because that achieves a lower energy state than when those atoms or molecules were separate. For the intermolecular forces, the main thing I want you to understand is that they are between molecules and help explain the physical state, solid, liquid, or gas, and may not be directly related to chemical properties or chemical reactions. Thank you for watching, and see you soon.